Hi everyone, we're going to report about geothermal power plant.
Renewable Energy 101. If you've ever observed an erupting volcano or the geysers at Yellowstone National Park, you've seen geothermal energy in action. The Earth's crust is made of rocks and water. Deep below that is a layer of hot, molten rock called magma, which is even hotter than the sun's surface. The heat just over 6 miles below the surface contains 50,000 times more energy than all the oil and natural gas resources in the world. Releasing a small amount of that heat in the right way can create electricity. A well drilled a couple of miles deep can capture the rising hot water and steam. That steam spins a turbine, and a generator produces electricity. Geothermal is one of the least explored sources of renewable energy in the US, and most of us probably don't spend much time thinking about it. But since it's a pollution-free, renewable source of energy that's consistently reliable, at least it has been for the past 4.5 billion years, maybe we should.
Geothermal power plants are used in order to generate electricity by the use of geothermal energy. They essentially work the same coal or nuclear power plant, the main difference being the heat source. With geothermal, the Earth's heat replaces the boiler of a coal plant or the reactor nuclear plant. Geothermal power plants require high temperature hydrothermal resources that come from either dry steam wells or from hot water wells. So geothermal refers to producing energy from heat the Earth. The internal heat the Earth generated from radioactive decay, minerals, and continual heat loss from the Earth's original formation. Geothermal wells are drilled approximately a deep 3 to 10 kilometers. The heat is extracted with a variety of methods, but in most cases drawn using water and steam. Hot water from the earth extracted by pumping it through the heat exchanger that transfer the heat into the building. Geothermal heat can also be used in producing electricity in a geothermal power plant. Electricity is generated when geothermal heat uses steam that turns turbines on a generator. The major regions of regional development are in the most volcanically and tectonically active regions of the world, though geothermal energy is currently a small player in the world's energy mix. One of its key advantages is its reliability and consistent power generation, which means it can provide baseload electricity. Concerns with geothermal include the accidental release of CO2 and hydrogen sulfide emissions stored in the earth groundwater that is often to carry geothermal heat to the earth's surface. Additionally, drawing heat from the earth's crust can lower down the earth's temperature below the surface if done responsibly. So here are some geothermal power plants in the Philippines. Tiwi Geothermal Power Plant in Tiwi, Albay. Macban Geothermal Power Plant in Calauan, Laguna. Calaca, Laguna. Tungunan, Leyte. Baguio City, Negros Occidental. Valencia, Negros Oriental. And Bacon, Sorsogon. So, in the past, taking advantage of geothermal energy was limited to areas where hot water flowed near the surface. But as geothermal technologies advance, we can leverage even more of these natural renewable energy resources. Engineers have developed a few different ways to produce power from geothermal wells drilled into the ground. So first is the dry steam. So dry steam is a geothermal power plant, and it's the most common type of geothermal technology used today. Underground steam flows directly to a turbine to drive a generator that produces electricity. Next is the flash steam. Flash steam power plant. A pump pushes hot fluid into a tank at the surface where it cools. As it cools, the fluid quickly turns into vapor or flash, vaporizes. The vapor then drives a turbine and powers a generator. The last is the binary cycle. It uses two types of fluid. Hot fluid from underground heats a second fluid, called a heat transfer fluid, in a giant heat exchanger. The second fluid has a much lower boiling point than the first fluid, and so it flashes into vapor at a lower temperature. When the second fluid flashes, it spins a turbine that drives a generator.
So there are three types of geothermal power plants. First is dry steam plants. These plants use dry steam that is naturally produced in the ground. This steam travels from the production well to the surface through a turbine. And after transferring its energy to the turbine, it condenses and is injected back into earth. These types are the oldest type of geothermal power plants. The first one was built back in 1904 in Italy. Because this type of power plant requires a high temperature, they can only be used where the temperature underground is quite high. But this type requires the least fluid flow. The next type is the flash steam plants. These types are the most common due to the lack of naturally occurring high quality steam. In this method, water must be over 180 degrees Celsius, and under its own pressure, it flows upward through the well. This is a lower temperature than dry steam plants. As its pressure decreases, some of the water flashes to steam, which is passed through the turbine section. The remaining water that did not become steam is cycled back down into the well and can also be used for heating purposes. The cost of this system is increased due to more complex parts. However, they can still compete with conventional power sources. The third type is the binary cycle plants. Binary power plants are expected to be the most commonly used type of geothermal power plant in the future, as locations outside of the known hotspots begin to use geothermal energy. This is because binary cycle plants can make use of lower temperature water than the other two types of plants. They use a secondary loop, hence the name binary, which contains a fluid with a low boiling point, such as pentane or butane. The water from the well flows through a heat exchanger, which transfers its heat to this fluid, which vaporizes due to its low boiling point. It is then passed through a turbine, accomplishing the same task as steam. So, the advantages and disadvantages. The advantages of geothermal energy. First, environmentally friendly. First and foremost, geothermal energy is extracted from the earth without burning fossil fuels, and geothermal fields produce practically no emissions. What's more, geothermal energy can be very beneficial, as you can achieve saving of up to 80% over conventional energy usage. Second, it's renewable. Geothermal energy is a source of renewable energy that will last until the earth is destroyed by the sun in around 5 billion years. The hot reservoirs within the earth are naturally replenished, making it both renewable and sustainable. And the third is, it is stable prices. Simple power plants depend on fuel, so the cost of the electricity is varying based on the market price of fuel. Since geothermal power plants do not use fuel, they do not need to take into account its cost, and they can offer their customers stable electricity costs. Fourth is heating and cooling. Effective use of geothermal for electricity generation requires water temperatures of over 150 degrees Celsius to drive turbines. Alternatively, the temperature difference between the surface and a ground source can be used, due to the ground being more resistant to seasonal heat changes than the air. It can act as a heat sink source with a geothermal heat pump just 2 meters below the surface. And the fifth is, it's reliable. Energy generated from this source is easy to calculate since it does not fluctuate in the same way as the other energy sources, such as solar and wind. This means we can predict the power output from a geothermal plant with a high degree of accuracy. Next is it is no fuel required. Since geothermal energy is a naturally occurring resource, there is no fuel required, such as with fossil fuels that are finite resource, which needs mining or otherwise extracting from the earth. Seventh is little to no geothermal system maintenance. Due to the fact that geothermal systems only have few movable parts, which are sheltered inside a building, the lifespan of geothermal heat pump system is relatively high. Heat pumps pipes even have warranties of between 25 and 50 years, while the pump can usually last for at least 20 years.
What are the disadvantages of geothermal energy? First, location restricted. The largest single disadvantage of geothermal energy is that it is location specific. Geothermal plants need to be built in places where the energy is accessible, which means that some areas are not able to exploit this resource. Of course, this is not a problem if you live in a place where geothermal energy is readily accessible, such as Iceland. Second, environmental side effects. Although geothermal energy does not typically release greenhouse gases, there are many of these gases stored under the Earth's surface which are released into the atmosphere during digging. While these gases are also released in the atmosphere naturally, the rate increases near geothermal plants. However, these gas emissions are still far lower than those associated with fossil fuels. Third, possibility of depletion of geothermal sources. Furthermore, despite being considered as sustainable and renewable energy, the chances are that specific location might cool down after time, making it impossible to harvest more geothermal energy in the future. Fourth, high investment costs and geothermal system. Another disadvantage is the high initial cost for individual households. The need for drilling and installing quite a complex system makes the price climb quite high. Nevertheless, the return on such investment is very promising, being able to earn the investments back within 2 to 10 years. Fifth, sustainability. In order to maintain the sustainability of geothermal energy, fluid needs to be pumped back into the underground reservoir faster than it is depleted. This means that geothermal energy needs to be properly managed to maintain its sustainability. Pollution contribution and control. Geothermal power plants have low emission levels. Unlike other power plants, geothermal power plants do not burn fuel to generate electricity, but they may release small amounts of sulfur dioxide and carbon dioxide. Geothermal power plants emit 97% less acid rain causing sulfur compounds and about 99% less carbon dioxide than fossil fuel power plant and of similar size. Hydrogen sulfide is the pollutant of greatest concern for geothermal power plants. One way geothermal power plants avoid this problem is by installing hydrogen sulfide abatement system, which can remove up to 99.9% of the hydrogen sulfide that will be released into the atmosphere. Most geothermal power plants inject the geothermal steam and water that they use back in the earth. This recycling helps to renew the thermal resource and to reduce emissions from geothermal power plants. Designing of geothermal power plant. So first, pipe sizing. M sub 2 equals density sub S, velocity sub S times pi d squared over 4, where d sub S is equal to inner diameter of the steam pipe, density sub S equals density of the steam, V sub S equals to velocity of the steam. Steam pressure drop delta P between well pad B and the power plant is calculated as delta P equals to density times gravity times delta Z times H sub L head loss times 10 to the power of negative 5 with head loss equals to d gamma times L sub S over D sub S times V squared over 2G, and 1 square root of F equals to negative log epsilon times D sub S over 3.7 plus 2.51 over RE, Reynolds number square root of F. RE equals density times V times D sub S over mu sub S, where delta Z is equal to elevation difference between well pad B and the power plant location,
H sub L is equals head loss. D gamma is equals friction factor for turbulence flow. Pipe roughness. R equals Reynolds number. Power output of the turbine. W turbine equals M sub 2 H times H sub 2 minus H sub 4 times eta sub S, where M sub 2 equals steam mass flow, when eta sub S is the isentropic efficiency of the turbine. H sub 2 and H sub 4 equals the inlet and outlet enthalpies respectively.
Condenser heat transfer calculation. Q is equals to M sub 2 times H sub 4 minus H sub 5, where H sub 4 and H sub 5 is equals to enthalpies into and out of the condenser respectively. Water mass flow rate in the condenser. Mass flow rate is equals to Q all over C sub P times T sub 2 minus T sub 1, where C sub P is equals to specific heat of the water and T sub 1 and T sub 2 is equals to inlet and exit temperatures respectively. Pressure drop is given in terms of head, which is related to the pressure loss. Pressure loss is equals to density times head times gravitational constant over conversion factor, which is 1 Newton meter per kilogram is squared. Gas removal system. Some geothermal power plants use steam jet ejectors to extract non-condensable gas. For high performance, non-condensable gas extraction will be achieved by using an electrically driven vacuum pump. The power of the vacuum pump is calculated by the power equation, where P sub V pump is equals to power of the pump in kilowatts. Gamma is equals to heat capacity ratio Cp gas over Cv gas. M sub G is equals to mass flow rate of the gas in kilogram per second. R sub U is equals to 8.314 kilojoules over K mole Kelvin, the universal gas constant. T con is equals to temperature of the condensate in terms of Kelvin. Mu sub V pump is equals to efficiency of the pump. M sub gas is equals to molar mass of the gas. P atmospheric and P condenser is equals to atmospheric and condenser pressure respectively. Cooling system. The function of a cooling tower is to decrease temperature from the inlet to the outlet of the tower based on the temperature between the warm water inlet and the ambient temperature. An efficient cooling tower will give a high temperature difference between the inlet and outlet water with a low temperature difference between the inlet water and the ambient temperature. Wet cooling tower calculations. Phi is equals to P sub V over P sub sat. Dry bulb temperature is the temperature of the air as commonly measured and used. Wet bulb temperature is the temperature of the air measured cyclometrically. If the air is saturated, Phi is equals to 100%. The wet bulb temperature equals the dry bulb temperature. Approach is the difference between the cold water temperature and the wet bulb temperature of the outside air. Range is the difference between the hot water temperature and the cold water temperature. Relative humidity is the partial pressure of water vapor in the air divided by the partial pressure of the water vapor that would saturate the air at its temperature. Or humidity ratio is the air per unit mass of dry air. Or omega is equals to 53.3 P sub V over 85.7 PA is equals to 0.622 PV all over P minus P sub V, where 53.3 and 85.7 are the gas constant for dry air and water respectively. Energy balance. Figure 8 shows energy balance in a cooling tower. To define the energy balance, the following variables are used. For the water, W sub A is equals to mass of hot water entering the cooling tower in terms of kilogram. H sub Fa is equals to enthalpy for the liquid entering the cooling tower in terms of joules per kilogram. W sub B is equals to mass of cold water exiting the cooler tower in terms of kilogram. H sub Fb is equals to enthalpy for the liquid exiting the cooling tower in terms of joules per kilogram. For the air, H sub A1 is equals to enthalpy for the cold dry air at 20 degrees Celsius joules per kilogram. Omega 1 is equals to humidity ratio for the cold air. H sub G1 equals enthalpy of the cold water vapor joules per kilogram. H sub A2 equals enthalpy of the dry air 40 degrees Celsius times joules per kilogram. Omega 2 is equals to humidity ratio for the hot air. H sub G2 is equals to enthalpy of the hot water vapor joules per kilogram. Following psychrometric practice, the equation for a unit mass of dry air can hence be written as H sub A1 plus omega 1 times H sub G1 plus W sub A times H sub FA is equals to H sub A2 plus omega 2 times H sub G2 plus W sub B times H sub FB. Mass balance. The dry air goes through the tower unchanged. The circulating water loses mass by evaporation. The water vapor in the air gains mass due to the evaporated water. Thus, based on a unit mass of dry air, omega 2 minus omega 1 is equals to W sub A minus W sub. This results the energy balance equation. Omega 1 times H sub G1 plus W sub A times H sub FA is equals to C sub P times T2 minus T1 plus omega 2 times H sub G2 plus W sub A minus omega 2 minus omega 1 times H sub FB, where Cp is equals to specific heat of air and T2 minus T1 is equals to temperature difference between inlet and exit air temperature through cooling tower. Power of fan. So this is the formula to calculate the power of the fan in terms of watts at the cooling tower. Next is the power of the pump. So the following equations are used to calculate the power of the pump. Thank you.